Hello and welcome. This is a video on limits and Leopital's rule, or at least that's how I say it. Some people say Lehospital's rule. That's probably even worse than the way I say it. I believe it's French, after a French mathematician, if I'm not mistaken. But anyway, it's a very useful rule, which basically just says that if you have a limit and you plug in the limit that the value that they give you for the limit, and you get an indeterminate form, you can just take the derivative of the numerator and denominator until you don't get it in an indeterminate form. Okay, so Leopital's rule says if a limit has an indeterminate form, and usually the indeterminate form is going to be 0 over 0. So that's usually, you're going to end up with 0 over 0. That's called indeterminate because you can't determine what 0 over 0 is. It's a little different from undefined. But anyway, if you have an indeterminate form, you can repeatedly take the derivative of the numerator and the denominator until you get an actual real number, and then that real number is going to be the value of the limit. And I believe it even works for infinite limits. So if it's not a real number, you might get like positive infinity or negative infinity. Okay? So if a limit has an indeterminate form, repeatedly take the derivative of the numerator and denominator. So you're going to be taking the derivative on the top and the bottom. Until the limit is no longer an indeterminate limit. So it's no longer in an indeterminate form. Okay, so take the derivative of the top and the bottom until the limit is no longer indeterminate. Okay, so you're going to end up with either a real number or positive or negative infinity. So that value of the limit then is going to be whatever you're left with after you've taken the derivative repeatedly. Okay, and by repeatedly I mean you take the derivative once, you plug in the number again, see if it's still indeterminate. And if it is still indeterminate, you take the derivative of the top and the bottom again. So you just keep doing it until you get a limit that's not indeterminate. And then the value of that, when it's not indeterminate, is the same as the value of the original limit. Okay, so the value of the resulting limit is the same as the value of the original limit. And it's called a rule because it always works. So Leopital's rule always works as long as the top and the bottom, when you plug in the value that they give you, as long as you get 0 over 0, or some of the other indeterminate forms include infinity over infinity. That's also considered an indeterminate form. But we won't be seeing that much in this section. In fact, it doesn't show up much in this particular book, at least not in this area. Okay, so let's see some examples. So even if you don't remember all the stuff about limits from Calculus 1, Leopital's rule makes a lot of limits from Calculus 1 just a piece of cake, because you don't have to factor, you don't have to try to rationalize a square root or radical expression. It just makes it so you can sort of mindlessly take the derivative of the top and the bottom until you actually get a limit that's a real number, or infinity or negative infinity, and then that's going to be your answer. So it's really nice. It's pretty easy, as long as you're good at taking derivatives. So example, find each limit using Leopital's rule. Using Leopital's rule. And I've never taken a French class, so I'm not claiming that I'm saying it right. So if you want to just call it Leopital's rule, that's fine. Some people just call it the hospital's rule. They added an S there. Okay, so for the first one, we're going to start with a relatively easy problem. Okay, so number 1, we want to find the limit as x approaches 3. The limit as x approaches 3 of 5x minus 15 all over 2x squared minus 18. The limit as x approaches 3 of 5x minus 15 all over 2x squared minus 18. So now to use Leopital's rule, you do have to plug in the number they give you and verify that it gives you 0 over 0, or rarely infinity over infinity. Okay, so plugging in the number is always the first thing you do when you're taking a limit. You should hopefully remember that from Calculus 1. So first you plug in. And what are we plugging in? We're plugging in 3 everywhere we're seeing x. And then that's how you see if a limit is indeterminate or not. So we plug in 3 here, so we're going to have 5 times 3 minus 15 all over 2 times 3 squared minus 18. And that should be familiar, hopefully, from Calculus 1. That's the first thing you do when you're finding a limit. It's called substitution. You just substitute the value of the limit in there and see what it gives you. So if we do that here, on the top, we're going to have 5 times 3 is 15 minus 15, which is 0 on the top. And then on the bottom, 2 times 9 is 18. So 18 minus 18 is also 0 on the bottom. Okay? So once you get 0 over 0, that means that's indeterminate. And like I said, there are other indeterminate forms, but all the ones from this section and on your homework are of the form 0 over 0. Okay. But the other indeterminate form that's most common would be infinity over infinity. And you can still use Leopital's for that. Okay, so anyway, because it's indeterminate, we're going to use Leopital's rule, which basically says you just take the derivative of the top and the bottom, and then you plug in the number again. Okay, so Leopital's, or Lehospital's. So I'm just going to be taking the derivative of the top and the derivative of the bottom. So you're not going to use the quotient rule, though. So you're actually going to be just taking the derivative on the top and taking the derivative on the bottom separately, but you're not using a quotient rule. It's not like that. Okay, so on the top, the derivative of 5x is just 5. And then on the bottom, the derivative of 2x squared, we're going to have to go ahead and use the power rule. So we're going to bring the 2 out front and decrease the exponent by 1. So we get 2 times 2 is 4x on the bottom. So we actually have 5 over 4x. And of course, I didn't write negative 15 or negative 18 because the derivative of a constant is 0. So that's why the negative 15 went away and the negative 18 went away. Okay, so far we should have 5 over 4x. So I did not use the quotient rule. I just took the derivative of the top and the derivative of the bottom sort of separately. And then what you do next is you still have to find the limit, but you take the limit as x goes to 3 of this new expression. And you can just keep doing this derivative on the top and the bottom until your limit takes either a real value or infinity or negative infinity. So plugging in here, we're going to be taking the limit as x goes to 3 of, I believe we said it was 5 over 4x. Yeah, 5 over 4x. Okay, so once again, you want to plug in 3, plug in again. Okay, but now we're plugging into an easier expression. So it's just 5 over 4x now. So plugging in, we have 5 over 4 times 3, which is going to be 5 over 12. So 5/12. This is not indeterminate. This is not indeterminate. I'm just going to write indet. Well, I could write a little bit more. I can write it over here. This is not indeterminate because to be indeterminate, you either have to be 0 over 0 or occasionally something weird like infinity over infinity. So that means this is our answer. So this is our answer. In other words, this is the value of the limit. So it's a really easy thing to do. You just take the derivative on the top and the bottom as many times as you need to until when you plug it in, it's actually a real number. It's not indeterminate. So here 5 over 12 is actually going to be our answer. Okay, so I'll go ahead and box that. Okay, and of course, if we had plugged in 3 and we still got 0 over 0, or infinity over infinity, then we would have to take the derivative of the top and the bottom again. And you have to just keep doing the derivative on the top and the bottom until it's something other than indeterminate. Okay? But it's a pretty simple process, and it's very effective, and it makes a lot of difficult limits from Calculus 1 just a piece of cake. Assuming you know how to do your derivatives, a lot of them just fall apart. They're just very easy. Okay, so let's see some more examples. Okay, problem number 2. So for this one, we're going to have a little bit more complicated polynomial. So for this one, we have the limit as t approaches -2 of t cubed minus 3t, t cubed minus 3t plus 2 all over t squared minus t minus 6. Okay, the limit as t approaches -2 of t cubed minus 3t plus 2 all over t squared minus t minus 6. And I apologize if my t's look like pluses. I've been trying to work on that, but sometimes they look like pluses. I think most of these are okay. Okay, so if you plug in -2, I'm not going to write it all out, but if you plug in -2, you're going to get 0 over 0 here. Because here you're going to have -2 quantity cubed, which is going to be -8. So you're going to have -8 minus 3 times -2 is going to be plus 6 plus 2 on the top. And then on the bottom, plugging in -2, we have -2 squared is going to be positive 4. Minus -2 is plus 2 minus 6. Well, what do you know? You get 0 over 0. That's indeterminate. I'll just write indet for an abbreviation. So this one is indeterminate. So once again, we can go ahead and do Leopital's rule. So we take the derivative of the top and the bottom. Here our independent variable is t, but other than that, it's just the same as the last problem. And here we're going to be using the power rule for each term. Okay, so Leopital's. So taking the derivative on the top and the bottom separately, we are not using the quotient rule. On the top, using the power rule, we're going to bring these powers out front. So we're going to have 3t squared minus 3 on the top, right? Because we bring the 3 out front, we decrease the exponent by 1, so that gives us 3t squared. And then the derivative of a constant times the variable is just a constant, so that's negative 3. And then over here, the derivative of a constant is 0. So the 2 just becomes 0. So on the top, we should have 3t squared minus 3. And then on the bottom, again using the power rule, we can bring this exponent out front. Okay, so we get 2t minus 1, right? Because the derivative of negative t is negative 1, and then the derivative of negative 6 is 0 because it's a constant. Okay, so what do? The limit is still as t approaches negative 2, so let me write that in. And each time you take the derivative on the top and the bottom, you do have to plug in the number again. I mean, if you can plug it in your head or on a calculator, whatever is fastest for you, you can do that, but you do have to plug it in and make sure it's, whether it's indeterminate or not. So with this one, if we plug in negative 2, okay, so plug in negative 2, we're going to get 3 times negative 2 squared, which is going to be, I'll just write it out. 3 times negative 2 quantity squared minus 3 over 2 times negative 2 minus 1. Okay, so on the top, negative 2 quantity squared is going to be positive 4. So we have 3 times 4 is 12. So we have 12 minus 3 is 9 on the top. And then on the bottom, we have 2 times negative 2 is negative 4 minus 1 is actually going to be negative 5. So we have 9 over negative 5. This one is not indeterminate because we don't have 0 over 0 or something weird like that. So because it's not indeterminate, this is going to be our answer. Okay, so the value of this limit is going to be negative 9 over 5. Remember, if you have a minus in the denominator, like 9 over negative 5, you can just bring the minus out front. So that gives you negative 9 over 5. Okay? But if that had been indeterminate, we would have had to take the derivative on the top and the bottom again. But we didn't, so we're good. Okay, cool. So let's see an example with trig functions. Okay, so this is example number 3. Now for this one, we want to find the limit as t goes to 0. The limit at t goes to 0 of 3 sine of 9t cubed, 3 sine of 9t cubed, all over 4t. All right, so what's new about this one is we have a trig function, but fortunately we're just going to be plugging in 0. So most people should remember how to take sine of 0. It's just 0. Okay, so anyway, if I plug in 0 here, I'm going to get 3 times sine of 0 on the top over 4 times 0 on the bottom. But sine of 0 is just 0. So we have 3 times 0 over 4 times 0, which is 0 over 0. So once again, we have an indeterminate form. So we're going to go ahead and use Leopital's rule. Now this one's a little bit trickier because the derivative's a little bit harder here. I just wrote le hop, the hop. Hop, yeah, that's it. Okay, so what we're going to do is we're going to have to use the chain rule to take the derivative of sine of 9t cubed. Okay, so we're taking the derivative on the top and on the bottom. The bottom is easy, the top is not so easy. So on the top, we're going to use the chain rule. Now recall that the derivative of sine is positive cosine. And because there's a 3 out front, that 3 is just going to stay out front. Okay, so we're going to get 3 times cosine, right, because the derivative of the outer function is cosine. And then you leave the inner function alone, so it's going to be 3 times cosine of 9t cubed. But then you have to multiply this times the derivative of the inside function. Okay, so that right there was just the derivative of the outer function. Inner left alone. So we're using the chain rule. Using the chain rule to take this derivative. And then now I take the derivative of the inner function. So the inner function is 9t cubed. That's our inner function. Okay, so for that one, we're going to go ahead and use the power rule. So we go ahead and bring the 3 out front, and 3 times 9 is 27, and then we decrease the exponent by 1, so it's going to be 27t squared. Okay, so we have times 27t squared. So that right there is the inner function. Well, it's the derivative of the inner function. So that's why they call the chain rule the outer inner rule, because you take the derivative of the outer function, inner left alone, and then you multiply that times the derivative of the inner function. But you can watch one of my earlier videos. I talk about that in detail. Okay, and of course we just took the derivative of the top. That was the tricky part. And then on the bottom, that's very easy to take the derivative of. The derivative of 4 times t is just going to be 4 on the bottom. Okay, so in our denominator, we're now just going to have 4. Okay, and then we can go ahead and keep writing the limit. We're still finding the limit as t goes to 0 of this whole thing. Okay, so we're taking the limit as t goes to 0 of this entire expression. And so what we're going to do here is we're going to just plug in 0 everywhere we see a t. So right there and right there. So what are we going to get when we plug that in? We're going to get 3 times cosine of 0 times 27 times 0 squared. All over 4. Well, in the numerator, remember that 0 times any other number is just 0. So up here in the numerator, we're just going to have 0. But in the denominator, we're going to have 4. Now, this is not an indeterminate form. Remember that 0 over a non-zero number like 4 is actually 0. Okay, so this is actually equal to 0, and this is not indeterminate. Okay, this is not indeterminate. So because of that, that's going to be the value of the limit. So our answer is actually going to be 0 here. The value of this limit is 0. Pretty cool, huh? Okay. All right, so let's do a couple more examples. Okay. So I believe that was number 4 that I just did. No, that was number 3. My bad. Okay, so that was number 3. This next one is going to be number 4. Okay, so for number 4, we have another limit as x goes to 0, but this time the function is going to be 11x squared all over cosine of x minus 1. Okay, so the limit as x goes to 0 of 11x squared all over cosine of x minus 1. Right, so as always, the first thing you do is you just plug in the number they gave you. Okay, so everywhere we see an x, we're going to replace that with 0 and see what that gives us. So on the top, we're going to get 11 times 0 squared, which is 0. And then on the bottom, remember that cosine of 0 is actually 1. So we're going to have 1 minus 1 on the bottom, which once again is 0. So we get 0 over 0. This is indeterminate, which means we go ahead and use Leopital's rule. Okay, so we're going to go ahead and use Leopital's. Now I'm getting so lazy, I'm just going to write L-H. That means Leopital's. Okay, and then, so we're going to be taking the derivative on the top and the bottom. So on the top, we use the power rule. So we go ahead and bring the 2 out front, and we decrease the exponent by 1. So on the top, we're going to have 2 times 11 is 22x. And then on the bottom, the derivative of cosine of x is actually negative sine of x. So on the bottom, we should have negative sine of x. And then the derivative of negative 1, because it's a constant, is just 0. So you should now have 22x over negative sine of x. And we're taking the limit as x goes to 0 of this one. All right. So let's see what happens when we plug in 0 this time. So plugging in 0 on the top, we're going to get 22 times 0. And then on the bottom, we have negative sine of 0. Well, on the top we have 0, and on the bottom, sine of 0 is also 0. So this one is 0 over 0, which is still indeterminate. This one is still indeterminate. So if it's still indeterminate, that means you haven't found the limit yet. In fact, the way I like to think of it, maybe it's not 100% scientifically correct, but the way I like to think of it is if it's indeterminate, that means you haven't determined the limit yet. So you have to keep going. Okay, so what do? We do Leopital's again. Do Leopital's again. Okay, and like I said at the beginning of this video, Leopital's rule is nice because you can just keep doing it as many times as you need to. You could even do it 100 times if that's how many times it took you to get it to where it's not indeterminate. And of course, these days, there are computers that will do some of those things for you if it is something that crazy. Okay, but if we do Leopital's again, we're going to take the derivative on the top and the bottom. So on the top, the derivative of 22x is just 22. And then on the bottom, the derivative of sine is cosine, but there's still a minus there. Okay, so we're going to have negative cosine of x on the bottom. Okay, and it's still the limit as x goes to 0. So now it's the limit as x goes to 0 of 22 over negative cosine of x. Well, let's plug in 0 again and see what it gives us. So this is going to give us 22 over negative cosine of 0. But cosine of 0 is actually 1. I don't know if you remember that. So we actually have negative of 22 over 1, okay, which is negative 22. And because this is not indeterminate, that means it's our answer. Okay, so that means the value of the limit is negative 22. So I'll box that. Pretty cool, huh? So that time we actually had to do Leopital's twice. And I know some of the earlier problems you might have been able to do it using techniques from Calculus 1, but for this one, This one would be pretty difficult to use any of the techniques from Calculus 1, other than maybe finding the limit graphically, but, you know, I kind of think of that as cheating. If you're using a computer or a calculator to find the limit, you haven't really done the math. Okay. It's not technically cheating, but, you know, it takes the fun out of it. Okay, cool. All right, so I wanted to do a couple more. Okay, so let's take a look at example number 5. So for example number 5, we're going to be looking at the limit as theta approaches pi over 2. The limit as theta approaches pi over 2 of 1 minus sine of theta all over 7 plus 7 cosine of 2 theta. Okay, so let me say that again. The limit as theta approaches pi over 2 of 1 minus sine of theta all over 7 plus 7 cosine of 2 theta. So kind of a complicated expression there. But it's not too bad. So as always, first thing you do is you plug in the number they gave you. So we're going to plug in pi over 2 everywhere we see a theta, and we'll see what that gives us. So we're going to have 1 minus sine of pi over 2 all over 7 plus 7 cosine of 2 times pi over 2. Okay, so that's interesting. So on the bottom, the 2's are going to cancel inside of the cosine. So we're actually going to have cosine of pi on the bottom. And then on the top, I don't know if you remember this from the unit circle, but pi over 2 is actually the same as 90 degrees. Okay, and there sine is going to be your y value, which is positive 1. Okay, so this is actually going to be 1 minus 1 on the top. And then on the bottom, we're going to have 7 plus 7 times cosine of pi. But cosine of pi is the same as 180 degrees. And from the unit circle, it's the x-coordinate when you're on the negative x-axis, which is going to be negative 1. Okay, so that's going to be 7 times negative 1. And if you don't like the unit circle, you're welcome to use a calculator to do some of those trig functions if you don't remember it or you just don't feel like trying to memorize it again. Okay, so what we got here is 1 minus 1 on the top and then 7 minus 7 on the bottom. So this is going to give us 0 over 0, which once again is indeterminate. Okay, so of course, if it's indeterminate, easiest way to find the limit is usually to just take the derivative of the top and the bottom using Leopitals. Okay, so Leopitals, le hop, yeah. So for that one, on the top, the derivative of 1, because it's a constant, is just 0. And then the derivative of sine is positive cosine, but there's a minus in front of it. So it's actually going to be negative cosine on the top. Okay, so on the top, you should have negative cosine of theta. And then on the bottom, the derivative of 7, because it's a constant, is 0. And then the derivative of 7 cosine of 2 theta is a little bit harder. Because this is a composite function, we have to use the chain rule. Okay, so our outer function here is cosine, and our inner function is 2 theta. So we take the derivative of the outer function, inner left alone. Okay, so over here we're going to have 7 times, well, the derivative of cosine is actually negative sine. Okay, so it's going to be 7 times negative sine of 2 theta. That was the derivative of the outer function, inner left alone. So in blue there I have the outer function. And then we multiply this times the derivative of the inner function. So here our inner function is 2 theta. So the derivative of 2 theta is just going to be 2. So it's going to be times 2. Okay. And then, of course, this is still a limit. We're still finding the limit as theta approaches pi over 2 of this whole thing. So let me give myself some room and write that in. Okay, so limit as theta approaches pi over 2. All right, and we can simplify this a little bit first, though. So these minuses are going to cancel out. There's a minus on the top and a minus on the bottom, so those cancel out. Okay, and then on the bottom, 7 times 2 is 14. So what we get here is the limit of cosine of theta on the top, and then on the bottom we have 14 sine of 2 theta. And this is still as theta goes to pi over 2. So what we're going to do is we're going to plug in pi over 2 again and see if we get indeterminate again. Okay, so plug in again. So we're going to get, on the top, we're going to have cosine of pi over 2. And then on the bottom, we're going to have 14 times sine of 2 times pi over 2. 2 times pi over 2 on the bottom. So the 2's are going to cancel down there. So we're actually going to have sine of pi in the denominator. Okay, and then on the top, I don't know if you remember this, but cosine of pi over 2 is the same as the x-coordinate on the unit circle when you're at 90 degrees, which is 0. Because you're actually right on the positive y-axis there, so x is 0. So on the top here, we actually have 0. And then on the bottom, sine of pi is where you're on the negative x-axis, and the y-coordinate there is actually also 0. So on the bottom here, we actually have 14 times 0, which is 0. Okay, so unfortunately, we have indeterminate again. So what does that mean? Well, that means we just do Leopitals once more. Okay, so we're going to go ahead and do Leopitals a second time. So take the derivative of the top and the bottom. Okay, so on the top, the derivative of cosine of theta is going to be negative sine of theta. And then on the bottom, we're going to have to use the chain rule again. 14 is a constant, so it stays out front. And then the derivative of the outer function sine is positive cosine. So it's going to be 14 times positive cosine of 2 theta. So the outer function there is sine. The inner function is 2 theta. So right there, I took the derivative of the outer function, inner left alone, and now I'm going to multiply that times the derivative of the inner function. So that's going to be times 2. Okay, that's my cat's robotic litter box. I apologize if you can hear it in the recording. Oh well. Okay, so anyway, we're ready to go ahead and plug stuff in again. We just might want to simplify it a little bit. Okay, so let me simplify this just a little bit. So we're going to have the limit as theta approaches pi over 2 of, on the top we have negative sine of theta, and then on the bottom 14 times 2 is 28. So on the bottom we have 28 times cosine of 2 theta. Okay, and then what do we do from here? Well, all we really have to do at this point is plug in once again, and hopefully we won't have to take the derivative a third time. Okay, so plugging in once again, plug in pi over 2. On the top we get negative sine of pi over 2, and then on the bottom we get 28 times cosine of 2 times pi over 2. So on the bottom the 2's cancel. Alright, so either using the unit circle or a calculator, on the top we're going to have negative sine of pi over 2. Well, sine of pi over 2 is the same as the y-coordinate when you're at 90 degrees. on the positive y-axis, so that's going to be positive 1. But there's a negative in front of it, so we're going to have a negative 1 on the top, and then on the bottom we have 28 times cosine of pi. Now, pi is 180 degrees, which is on the negative x-axis, and cosine is the x-coordinate, which is negative 1. So in the denominator, we're going to have 28 times negative 1. Okay, so finally, on this problem, we don't have 0 over 0, so this is not indeterminate. So here, these minuses cancel out on the top and the bottom, and we're left with 1 over 28. And because this is not indeterminate, that means it's the value of the limit. Okay, so the value of this limit is going to be 1 over 28. Pretty cool, huh? All right. Okay, so I want to just do one more harder problem to hopefully prepare you for all of my homework. Okay, so problem number 6. My computer's acting a little bit slow right now. I hope the recording comes out okay. Okay, problem number 6. For this one, we want to find the limit as x approaches 0 of x squared over ln of secant of x. Okay, the limit as x approaches 0 of x squared over natural log of secant of x. So that's an interesting problem. So for this one, basically what we have to do is, as usual, first we plug stuff in. But it might be a little hard to plug stuff in, so you might have to try to remember a few things. You're also welcome to use a calculator to plug stuff in. Okay, but first we're going to plug in 0 everywhere we see an x. Okay, so on the top we're going to have 0 squared. On the bottom we're going to have ln of secant of 0. Now, I don't know if you remember this, but secant is actually the same as 1 over cosine. So instead of writing secant of 0, I'm going to skip ahead and just go ahead and write 1 over cosine of 0. Okay, because secant is 1 over cosine. And then what's cosine of 0? Well, it's the x-coordinate when you're at 0 on the unit circle, so that's just going to be 1. Okay, so that's interesting. So what we have here is on the top, 0 squared is 0, and then on the bottom we have ln of 1. Now what is natural log of 1? Remember, ln, or natural log, is the same as log base e. Okay? And log base e of 1 is the same as asking, well, e to what power gives me 1? Actually, e to the 0 gives you 1. So that's going to be 0. Okay? So we're going to have 0 over 0, which is indeterminate. But we kind of expected that since it said to use Leopital's rule, right? The first one had to be indeterminate to even use the rule. Okay, so since it's indeterminate, we're going to go ahead and take the derivative of the top and the bottom. That is my son crying, but my wife is taking care of him, hopefully. Okay, so what we got here is we need to take the derivative on the top and the bottom. So using Leopital's, on the top, taking the derivative using the power rule, we bring the 2 out front and we decrease the exponent by 1, so we get 2x. And then on the bottom, we actually have to use a chain rule. So on the bottom, the derivative of the outer function, ln, is going to be 1 over. Okay, so here our outer function is natural log, and our inner function is secant. So we take the derivative of the outer function first, inner left alone. So the derivative of ln is 1 over. So that's going to be 1 over secant of x times the derivative of the inner function. So what's the derivative of secant of x? Oh, it's been a while. You know, you can always go to I do include a formula sheet that I compiled over the years, and it should be in one of your modules. You just go on and look at it. But the derivative of secant of x, I believe, is secant of x times tangent of x. Okay, so secant of x times tangent of x. So in the denominator, we're going to have 1 over secant of x times secant of x times tangent of x. I'm going to go check on my baby. And just pause this for a second. Yeah, so he was just having his diaper changed. So I'm back here. Okay, so anyway, the derivative of secant is secant times tangent. And like I was saying, you can just go to our modules. It's either in the week 2 or the week 3 module, depending on which course you're in with me. But you just go onto Canvas and you can download the formula sheet. It's called Formulas from Calculus 1 and Calculus 2. Let's see. Here it is. For this particular course, it came in week 3. Formulas from Calculus 1 and 2. You download that PDF. And then you open that up. And it's got all kinds of nice formulas in there, just in case you start forgetting them, because there's so many formulas in calculus. And I also let people use these during the test, which is probably a little too easy, but that's what I do. Okay, so anyway, what we're looking for is the derivative of secant of u, and I was correct. It is secant of u times tangent of u times du dx. So that's it right there. Okay, so let's go ahead and, well, I already did it correctly. So the outer function was ln, so I did 1 over the inner function, and then I did times the derivative of the inner function. Here the inner function was secant of x. So the derivative of secant of x is secant of x times tangent of x. Okay, and then in the denominator here we can see that the secant of x is cancel. So we're going to have 2x over tangent of x. So you have the limit as x approaches 0 of 2x over tangent of x. Limit as x approaches 0 of 2x over tangent of x. And somewhat conveniently, that entire natural log just went away when we took the derivative, which is kind of nice that they have it set up that way. Okay, but of course, what we have to do next is we have to plug in 0 again and see what it gives us. Okay, so if we plug in 0, on the top we're going to have 2 times 0, and then on the bottom we're going to have tangent of 0. Now, if you have a calculator, you can type in tangent of 0, or you can use the unit circle. It's just sine of 0 over cosine of 0. Well, sine of 0 is going to be the y-coordinate when you're at 0, which is going to be 0. And then cosine of 0 is actually going to be the x-coordinate, which is 1. In other words, tangent of 0 is going to be 0 over 1, because sine of 0 is 0 and cosine of 0 is 1. And then 0 over 1 is actually 0, though. And the reason I'm writing it out is in case you get confused about these things. So sine of 0 is 0, cosine of 0 is 1, but on the denominator here, 0 over 1 is the same as 0. So this is actually going to give us 0 on the top and 0 on the bottom, which is indeterminate. Indeterminate. I'll finally write it out for this one. Okay, so if it's indeterminate, you have not determined the value of the limit yet, which means what do? You take the derivative of the top and the bottom again. Okay, so we apply Leopital's rule once again. Okay, so Leopital's rule once again. All right, so then on the top, the derivative of 2x is just going to be 2. And then on the bottom, the derivative of tangent is secant squared of x. I remember that one. Remember that one for sure. But again, you have that formula sheet. Derivative of tangent is right here. secant squared of u times du dx, but here it's just tangent of x, so it's just going to be secant squared of x. Okay? So on our denominator here, we're going to have secant squared of x. All right, and this is still the limit as x approaches 0. So we want to find the limit as x approaches 0 of 2 over secant squared of x. So we're plugging in 0 everywhere where we see an x. Okay, and remember that secant is 1 over cosine, so secant squared is 1 over cosine squared. So now I'm going to go ahead and plug in a third time. So we're going to have 2 over secant squared of 0. But like I was just saying, secant is 1 over cosine, so secant squared is 1 over cosine squared. Okay, so this is the same as 2 over 1 over cosine squared of 0. And what does cosine squared of 0 mean? It's really the same as cosine of 0 quantity squared. And what is cosine of 0? Well, it's the x-coordinate when you're at 0 on the unit circle, which is 1. Okay, so this actually gives us 2 over 1 squared. But 1 squared is just 1, and 1 over 1 is 1. So we get 2 over 1, which is 2. And because this one is not indeterminate, we know we're done doing Leopital's rule. So because this one is not indeterminate, that means it's our answer. So the value of this limit is actually going to be 2. Okay, so this equals 2. All right, and that finishes this lecture. Thanks for watching.